Watching kids.
What we're doing today is, and tomorrow, is chapter 4, cyclic groups. This should be blue. Right. So you've seen some examples of cyclic groups and some of groups. Right. And what Killian told you is a group is something, you have a set, and it has these axioms. Now, an example was non-zero rational numbers, perhaps, and non-zero real numbers, and multiplication, for example. And there was all real numbers and addition. And these things look like, and then there was and then there was another example, I think, symmetries of the square. So there is a slight difference somehow between the reals and addition and symmetries of the square, in that symmetries of the square are sort of like transformations. You know, they take something and do something with it. Whereas the numbers don't necessarily do it. But I find it very useful when you think about all groups as some sort of transformations. So a group element essentially is like an operation that does something. And then multiplying or adding, if you're using the additive notation, group element is like composing these transformations. It's a very useful point of view. So when we're talking, okay. Yeah, so but you can also think of the real numbers and addition, for example, as you take all the real numbers and you shift them by that number. Okay, so a number 3 corresponds to shifting all real numbers to the right by 3. Number -7 minus 7.3 corresponds to shifting everything. So it's again a transformation. It takes all the real numbers, puts them somewhere. Just like you have with the square, you can flip it or you can rotate it. So it's something that acts on the square. And think of the real numbers as acting on the real numbers themselves by shifting them. And then when you shift something by 3 to the right and by 7 to the left, you get 3 minus 7 minus 4. So the effect is the same as shifting it by 4 to the left. Okay, so this is the composition of the transformation, which corresponds to adding real numbers. And the multiplicative group of real numbers, think of it as stretching or squeezing. So if you get, so the number 2 would correspond to stretching everything by 2. So 1 goes to 2, 2 goes to 4, and so on. And 1/3 corresponds to squishing it. But it's not non-zero, it's only the positive real numbers. But if you added the negative real numbers into the multiplicative group, you get a stretch and combined with a flip. So it's like, so again, so really you're multiplying numbers, but think of it as stretching and squeezing. This is, I just wanted to make this point to Killian's lectures, because it's, I'll refer to it sometimes, probably. Okay. Now, what is a cyclic group? Okay, so, I don't know what I'm going to say. Okay, so the book says you should look at the example 3 times z, which is the set of all the multiples of 3, integer multiples, so say 0, 3, 6, and so on, with addition. So this is a subgroup. Of integers with addition. So integers with addition is just all integer numbers adding. The inverse is the negative. 0 is the identity. This is a subgroup. How do you know that something is a subgroup? Presumably you have those theorems that tell you how to
contains the identity.
Yeah. So if this does contain the identity, if you add 2 multiples of 3, you get a multiple of 3, and it has all inverses because if 1 is a multiple of 3, then the negative is also a multiple of 3, so that's a subgroup. Now, this subgroup here is somehow determined by the number 3. It's determined in the sense that if you have a subgroup of Z that contains 3, then you have to have all multiples of 3 as well, because otherwise it wouldn't be a subgroup. And so by adding the 3 with itself, you get all the positive ones. Well, you have to have the 0, because the identity has to be there. You have to have the negative of 3, because you have to have inverses. And by adding minus 3 with itself, you get all the negative multiples. So there's no way of getting a subgroup of Z containing 3, which doesn't contain all these numbers. So in this sense, 3Z is the smallest subgroup of Z containing 3. Okay, and that's something called. We'll come to that in a properly later. This is called that. This subgroup is generated by 3. So it's a subgroup of Z generated by 3. 3 just gives them. And at the same time, it's just you can start with the 3 and take inverses and zeros and keep adding, and you get all the elements one day or another. So any element in this subgroup you can get by just adding 3 a sufficient number of times, or taking its inverse. So another example of a group like this is you have the D4, so that was the symmetries of the square. Yeah, number 9. Now, if you take all the rotations, what note does it mean? Is there any special notation for rotation? But well, anyway, rotations form a subgroup because if you rotate right left, so you get the inverse of the, well, the 0 rotation is the identity, so you don't rotate by 0 degrees. And if you rotate, well, so the inverse of a rotation is the opposite rotation, so that's also in the group. So we've got composers to rotations. So this is a subgroup. Okay, is it determined by a single element of D4 in the same way as this was determined by 3?
No. Not really.
It's the shape of the square.
No, I don't know. Well, the shape of the square determines the whole group. But my question is, when you take all rotations as a subgroup, is it determined from this by the same way as 3Z is determined from Z? Ah, it is. So if you take, for example, just a rotation by 90 degrees, what does 90 degrees mean? Like this? Now, if you keep adding the 90 degrees, well, if you keep composing the 90 degrees, you get 90, 180, 270, back to 0, and you get all the rotations by just composing the one rotation with itself and taking in the inverse. Okay? So this is a similar situation. Again, this subgroup is fully determined. Well, the proper word is generated by, I think they call it row 1 in the file, I can't remember, by 90-degree rotation. Or 270-degree rotation. Not 180, because if you take the 180, okay, it just rotates it fully and rotates it back, but you don't get the 90 from the 180. So this is called generated. Right, so the general phenomenon that's here is that in any group, if you take any single element and you take all its, and you just let it take its inverse and all its kind of powers or multiples, depending on whether it's additive or multiplicative, you get a subgroup. Okay, so here you took the 3. It's inverse, and then you just add them together in all possible ways. You get the whole of this, and it's a subgroup. And similarly, here, if you take one rotation and you keep composing it with itself, you get all the rotations, and that's a subgroup. And so this is theorem 4.3. All right. In the book, which says that if G is a group, and A is any element of G, then that's a theorem and a definition in one, which is a nice mathematical concept. Something that's denoted by the end brackets around the element it's all the powers, so the powers within the group, of course, using the operation of the group, of this element. So this is a subgroup of G. And then it also says that it is the smallest subgroup of G containing A. Among all the subgroups of G that contain A, that's the smallest one. Okay. Is that theorem clear what it says? Or not?
So why is it the smallest?
Because I have a proof.
Okay, I'm coming to that. Never mind.
So would you, well, hopefully you know what I mean by the smallest. The smallest means in terms of inclusion. So, so every other group, every other subgroup of G that contains A must contain this.
This
and all of this as well. So there are other subgroups containing A, perhaps, but they all contain all these elements. And that's kind of clear. I mean, I said it with the integers. I said, well, you have to have all the multiples of 3 if you have 3. Because if you keep adding it, then you just get all the multiples of 3. And you need the inverse of 3 to make it a group, a subgroup. So, so that the proof is really, in general, it's the same. That's what I said. So first, there are 2 claims. First, that this is a subgroup. Second, that it's the smallest subgroup. So being a subgroup, there is a proposition called 331. There are 2, 330 and 331. So I'll take the 331. In the book, they took 330, so you will have 2 different proofs. We need to show that. So this one says it has to be non-empty, or any. Whenever you take 2 elements in that subset generated by A, you have that when you take their product in the group, you get something that's also generated. Okay, so this one, first thing is obvious because A is there. And the second one is if, so when we have G and H in this generated subset, and where are they there? Well, this is defined as powers of A, and if G and H are both in this set, they both must be powers of A. So G is some power of A, H is some power of L. This is really a simple group, kind of algebraic proof where everything just follows from when you write it. So this is AK times, so A to the K times A to the L, which is A times M. This is A to the K plus L, which, again, by the definition of the bracketed A, is into bracketed A. Okay? This is what it does. So there is nothing fundamentally deep about it. It's just write the definition and you see it works. And for the smallest, to show that it's smallest, sorry, it's just too late to think. Show that A is the smallest subgroup containing we take H to be any subgroup of G. That's a subgroup. Killian used less than or equal to for subgroups. Okay. Well, H subgroup of G. So what we want to show is that
The C thing.
Yeah, can you do the H
The little-
bracket, G bracket?
No, it's the little, I don't know, like a C, a flat C.
Oh, the one that looks like that.
that's a subset,
That's
Oh, it's a subset.
which is not necessarily a subgroup. You can,
No.
never knew that.
So I wanted to, so this little squished C
Whatever that
is a mean subset. But what I want to say is it's a subgroup rather than just a subset of the elements.
Alright.
Okay, so it's a subset which is closed under all the operations. Where are we? Okay, so what do I want? Well, this one is the smallest, so what I'm claiming is that if H contains A and is a subgroup, it contains all of this. Now, well, they say this book is making a shortcut a little bit. Clearly, any subgroup H of G containing A must contain all the powers of A by closure. So it's obvious that you have to have all the powers of A. But if you wanted to prove it properly, you'd say, okay, by induction. So it contains A. I want to show that it contains A to the K for all positive K, positive integers K. So K equal 1, I already have. That's my assumption. And then for the induction step, if it contains A to the K, well, and A, which we know, I times them together, I get AK plus 1, so it has to be there as well. And I will do the same trick for the negative ones. So there's an induction proof hidden in the, it's obvious in the and by easy induction, A to the K is in H for all K greater than 0. A to the 0 is in H because it E, that's the identity, and it has to be the subgroup, otherwise it won't be a subgroup. A to the minus 1 is in H. Again, because well, and then from that, from the minus 1, A to the K is in H for K less than 0 by another induction. Easy induction. Make a side remark. Yeah, okay, that's the end of the proof. Because you complained about proofs by induction. So a proof by induction is a proof by contradiction in disguise, as I will now briefly demonstrate. So what I'm claiming is that A to the K is in H for all K greater than 0. Okay. Suppose not. Well, if not, then there is some A to the K which is not in H. So among all these elements, or among all these different Ks, I take the smallest one. So I have A to the K is not in H, and it's the smallest K with this property. So everything so A to the L for all L that are smaller than K is already in H. Okay? Now what is K? K can't be 1 because A to the 1 is in H, so K is not 1. Okay? So I look at K minus 1, that's less than K. So A to the K minus 1 is in H because K was the smallest one for which A to the K wasn't in H. So A to the K minus 1 is in H, but if I times it by A, I get A to the K. And it must be in H, so it's a contradiction. And every proof by induction works like this. Take the smallest counterexample, okay. And then by looking at the smaller things, you show that it can't be a counterexample. That's how induction works. From the principle, what's it called, the least well-ordered principle. So you can take the least then. Okay, we've got this proof. Next thing I need to tell you is where are we? So, definition. This is called the cyclic subgroup. Generated by me.
Already said generated, so that should be
Okay.
so-called generated. What does it
Say, and G is a cyclic group. If G has an element that generates the whole group. So if I can take one element that generates the whole group, then it's called a cyclic group. Some I'll do examples in a second. Case. Well, in this case, A is my A looks the same as my A. It's called a generator of G. And finally, the order of any A, so the is the least n for which if I take A times it with itself n times, I get the identity. Yeah, so if you take a generator of G, its order is the same as the order of G, because it generates the whole group entity. Okay, examples. So is that a cyclic group or not?
Yeah.
Why?
Generate everything with one.
Exactly. So Z is cyclic, generated by 1 or minus 1. Z 6. So 0, 1, 2, 3, 4, 5 modulo 6. Is that cyclic?
Yes.
Yes. And 5. Does 5 generated? Yeah, it should do, shouldn't it? So it's also cyclic, generated by 1 or minus 1, which is 5. There are some other examples. Example 4.5 that says that the order of 2 in Z6. So, for example, 2 does not generate Z6. Order of 2 in that group is, that's an exercise. But you can see it in the book as a cheat.
But if you didn't have the book, what would the order of 2 in Z6 be?
3.
Why is that?
2 to 3 is equal to the identity.
Yeah, but 2 to the 3 is 3 times 2 in this case. So 2 plus 2 is 4, plus 2 is 0 in Z6. So you take 2 3 times, you get the identity. And so the subgroup generated by 2 is 0 to 4 in Z6. Okay? Good. What else? There are some other examples. Have a look at examples 4.6 and 4.7 in the book. Well, explain the. I'll add one, which is that the D4 symmetries of the square, is it cyclic or not?
Yeah.
Is it? Give me a generator.
A 90-degree rotation.
Default is symmetry. How do you
Symmetries of the
symmetry?
square.
We're talking a perfect square as well, not a rectangle.
Square, yeah.
Right. Just double checking that because
That
last.
was not a
No,
A square is a square.
I know. I know that, Laura. I was defining because last week when Killian was talking about the rectangle, that you'd have to rotate it by 180 for it to be an identity, you know?
Yeah.
So each time that the square is rotated, it would be its own identity, wouldn't it? It just makes sense the same. So, yeah.
Doesn't matter though.
No.
Either one of them is. Okay. The answer is the same for both the square and the. So yeah. So you said yes. So prove it.
Paper.
Well, the symmetry of the square is just a square, so anytime you rotate it 90 degrees, you've already got its symmetry.
But I'm not talking about the square. Yeah, but not all the symmetries are generated by the rotation.
Oh, there's not all of it. The opposite is the.
Yeah. Because if you
Yeah,
You flipped it.
the kind of what's it called reflection.
yeah.
Reflection you can't get from no matter how many rotations you do, 90, 180 to 70, whatnot, you can never get that one. Okay, so no rotation generates the whole group of symmetries, and no single no single reflection generates the whole group either. But if you had 2 elements, if you took, let's say, 1 rotation and 1 reflection, you get the whole group already by using just these 2. And if you get two reflections, 1 vertically and 1 horizontally, then you also get all the rotations. But there's no single element that will generate the whole group, so this is not cyclic. Okay. Good. Any questions so far? Fun playing around. Okay, so the next thing that we want to do is a theorem. 4.9. It says that every cyclic group is abelian. I'm becoming dyslexic, and speaking. Is that a word?
Is that?
I like how that was both simultaneously the name of it and the symptom.
Every cyclic group.
I also have that.
this speaker. Oh my god, that was amazing.
Brilliant.
God.
Well, the book uses abelian with a little a, which probably.
Can we say something about like the first year saying that abelian should be capital A or be used little a?
Well, there are various schools of thought.
Depends whether it's a name.
It's supposed to be of someone, I think.
Yeah, it's Abel with a Norwegian mathematician.
That was yeah. Wasn't a.
Do you want to get enough time in my life? Hey, if it is capital on it. I think that would be the sense I take on it.
Really? So if you worked out some really mathematical equation, you would have it as a clay force, is it?
Yeah, I would, but I wouldn't care if you put a capital in. As long as it was my name and you knew it was my name, I think I'd be fine with it.
Really?
Okay, so what does abelian mean? As a reminder,
Oh,
commutative.
AB equals BA.
So commutative.
Community.
And the reason it's
Really got that.
abelian is that it really just the group operation really just boils down to the addition of the exponents of the generator. Okay, and addition of all numbers is commutative. So C. So G is the group generated by some element A, and G and H are in the group, and we want that they commute. Okay. So because G are in a group generated by A, that can't happen unless G is the generator to some power, because of the definition of a single group, and H is the generator to the same, possibly a different power, for some whole numbers A and L. Okay. But then what's GH? Well, GH is A to the K, A to the L. Well, that's nothing else but times with K times with itself. This speaking. And then L times, well, that's the same thing as doing it K plus L times once. But this, of course, I'm being too slow here, is this. Okay. Is that credible?
Makes sense.
That's algebra. Algebra is, well, in the beginning, algebra looks very easy because it's just plain. Everything just jumps off. But then the concepts are quite deep and captures those. Anyway, so that's a quite simple. Like I said, just boils down to the addition of the exponents. Okay. Yeah. I'm running out of time. So last theorem, and let's try to get the proof. So this theorem says that every subgroup of a cyclic group is cyclic as well. Every well, you take a cyclic group generated by one element, you take any subgroup, it will also be generated by one element only. Potentially some other element, because none of the generators of the original group is necessarily in the subgroup, but it's also cyclic. Yes. And therefore nice. Proof won't fit on this page. Proof won't fit here.
Okay.
So I'll probably start a new page.
Could you tell me that before I wrote it? Will it fit there?
Yeah, that will do.
That's okay.
We've only got 6 minutes. Have I given you the the sheet?
I need one, yeah, because I gave mine
Alright.
to
The
Matt.
I haven't got any.
Yes, I don't have to do it now.
I'll just do it and give it back to you.
Doesn't matter. You don't really need it. No. Okay, so next page. Let's see if we can get that.
Right, okay, that makes more sense.
Quickly. So proof. Remember, we have a cyclic group, G, so generated by one element, because it's cyclic, and H is a subgroup of G, and we want to prove that no matter what H is, it's also generated by a single element. Okay? So, well, what is G? G is all powers of A. H is a subgroup. So there is case 1 is that it's a subgroup, so it definitely contains the identity. It doesn't contain the identity, it's not a subgroup. If it is just the identity and nothing else, is it cyclic?
Yeah.
Yes, it's generated
Generated
by the identity. So that's okay. And otherwise, H contains A to the K, because everything in G is A to the K, for some non-zero K. It also contains A to the minus K, because it's a subgroup. Perhaps I don't know. Have we proved that A to the K inverse is the same as A to the minus K?
Some way.
Possible. But
It's A to the K to the minus 1.
but it is. So it contains the inverse of this, so it contains A to the minus K. Now, at least one of these numbers is positive. Either K is positive, or minus K is positive. So we can assume that K is positive. In other words, it contains a positive power of A. Now, and now comes the well-ordered property again. What do they use? M. Let M be the least positive integer such that A to the positive integer. Okay, this is stupid. I'll delete it. Let M be minimum K bigger than 0, such that A to the K is in that zone. Okay, so I look at all the positive exponents of A, positive powers of A, that live in the group, in the subgroup. And among them, I pick the smallest one, and I'll call this M. Okay. And my claim.
She did really good.
A to the M generates the group, the subgroup. Okay, but I still haven't proved it. I think we'll finish it tomorrow. Is it a good idea to stop in the middle of the proof?
Not if you're killing it. Not if you're killing it.
Depends if you can remember it tomorrow.
I can remember.
That's alright.
Maybe it's a piece of paper with red.
Who's killing usually gets all his proofs and copies of Billy and puts them on.
He just knows.
Well, yeah.
He knows every proof.
Okay, so we need to finish this proof. We need to finish this proof. What we're going to do after finishing this proof is,
Another proof.
yes, another proof.
Multiplicative
There are
proofs,
the
complex
theorem, or proposition 4.12, and then there's 4.13. We should have a look at. They're interesting. And then, as an example of cyclic groups in section 4.2, we have the multiplicative group of complex numbers. Which is a very interesting example because. So we'll do that. And if we have some time left at the end, which we won't have, then we can start doing the exercises in section 4.4. And then, again, you have two questions from section 4.4. The question 5 is relatively simple. Question 26 is relatively simple. We have these two to submit. Oh, has anybody brought anything to? Oh, we can say goodbye to people. Goodbye.